So dear students, in this lecture we will discuss one numerical which is related to the state regulator design. That is, the purpose is to determine the state feedback matrix, okay, for a system, discrete time system. So the example is given here. So we have a discrete time system which is given by this equation, wherein the matrix F is given here, which is 2 by 2 matrix, and matrix G is also given here, right? And the desired closed loop poles of the system are these, right? And it is given that we have to assume t is equal to 0.1 second, right? Now we have to find out the state feedback gain matrix such that it can locate, it can place the poles of the closed loop poles of, okay. So we have to find out k such that it can place the closed loop poles of the given system on the desired location, right? This is the desired location. So now our purpose is to find out the matrix K, state feedback gain matrix, right? And state feedback gain matrix is given by K is equal to minus K1 and K2 in this case, because here N is equal to 2. That is, the order of the system is 2, because this F is a 2 by 2 matrix, right? So let us solve this numerical and let us try to understand the concept also. Now, as the given system is xk plus 1 is equal to 0 t, sorry, not 0, uh, it is 1 t 0 and 1, and we have this plus we have t square by 2 and t and up. This is the state equation of the given system. Now the first step is to form the characteristic polynomial. This is the first step. The characteristic polynomial is actually zi minus f. So we have to form the characteristic polynomial of matrix f, right? So it is zi minus f. So zi minus f can be formed like this. So I is the identity matrix. This is the identity or unit matrix, right? So now it is 1 0 0 1, and then f is sorry, f is 1 t 0 and 1. So this would be z 0 0 z minus 1 t 0 1. So zi minus f is z minus 1 minus t 0 and z minus 1, right? Now the characteristic equation here is of the open loop is zi minus f is equal to 0. So this is actually an open loop characteristic polynomial, right? So zi minus f0, that means z minus 1 minus t0 z minus 1 is equal to 0. So this will give me z minus 1 whole square minus 0 is equal to 0. So z minus 1 whole square is equal to 0. So we get z square minus 2z plus 1 is equal to 0. So first thing is to form the characteristic polynomial. So characteristic polynomial is this, right? uh, and characteristic equation of the open loop system is this one. This is, for example, so let us mark these equations. So this is, for example, equation number 1, and for example this is equation number 2 here. Then we have the characteristic equation, for example this is 3, and this is, for example, 4. Now the second step here is, let us come to the step number 2. Now step 2 is, so we will form the closed loop characteristic equation. So the closed loop characteristic equation can be obtained by considering the control law. So the required control law is uk is equal to minus kxk, and because k is a matrix, state feedback gain matrix, which is k1 and k2, there are two elements in this xk. This is, for example, your equation number 5. Now if we substitute, uh, we have the, now we have this equation here with us, this equation number 1, or you can say this general equation. Okay, this is the standard equation. So if we substitute uk is equal to minus k xk in this equation, so we'll get the closed loop system, right? So the closed loop system is, so we have xk plus 1 is equal to fxk plus g and minus kxk. We have simply replaced uk with minus kxk here, so it will give me fxk minus g kxk, and hence I'll get xk plus 1 is equal to f minus gk into xk. This is, for example, equation number 6. Now, because we have to form the closed loop characteristic equation, so the uh, required closed loop characteristic equation is zi minus f minus gk is equal to 0. So this is the required characteristic equation of the closed loop system. Now how will we form? So we need to have f minus gk matrix. So f minus gk matrix can be obtained by putting f1 t0 1 and minus g is t square by 2 by t, and k is k1 and k2. So we can simplify this one. We have 1 t01 minus t square by 2 k1 t k1 t square by 2 k2 t k2. So we have multiplied this matrix with this matrix element wise, and we have got this particular matrix, right? So we can simplify this further. So we have 1 minus this. Okay, so we have 1 minus t square by 2 k1 t minus t square by 2 k2, 0 minus t k1, and 1 minus t k 2. So this is f minus gk matrix. So we can find out zi minus f minus gk matrix now. So which is z1001 minus f minus gk matrix is given 1 minus t square by 2k1 minus tk1 t minus t square by 2k2. So 1 minus tk2, right? So this will give me z00z minus 1 minus t square by 2k1 minus tk1 t minus t square by 2k2 1 minus tk2, right? So we'll simplify this one. So we have zi minus f minus gk is equal to, so we have z minus 1 plus t square by 2k1 k1t, and we have minus t1 plus t square by 2k2, and we have z minus 1 plus tk2, right? So this is, for example, our equation number, let us say 8. This is our equation number 8 here, right? Now the closed loop characteristic equation is, so we have the required closed loop characteristic equation is mod of zi minus f minus gk is equal to 0. So that means we have z minus 1 plus t square by 2k1 k1t t square by 2k2 minus t1 z minus 1 plus tk2 mod is equal to 0. So the determinant would be z minus 1 plus t square by 2k1 into z minus 1 plus tk2, right? Minus k1t, and we have t square by 2k2 minus t1. Not t1, sorry, it is t only, right? So it is also t here. So this is a typographic mistake, and yes. So we have this equation, we'll put it equal to this equation. We have z square minus z plus tk2z minus z plus 1 minus tk2 plus t square by 2 k1z, and then we have minus t square by 2 k1, then we have plus t cube by 2 k1 k2, then we have this one, then we will open this one. So minus t cube by 2 k1 into k2, then minus minus plus k1t square is equal to 0, right? So let us simplify this one. So we have a z term here, 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 right? So we can write z square minus 2z. You can see, so this is minus z in, and minus z. So we have minus 2z plus tk2z, and then we have plus t square by 2k1z, and we can see here these two terms will be cancelled out as it is. Then we have this is a constant term here, then this is also constant term here, this is also constant term here, and this is also a constant term here. So we'll write plus 1 minus tk2 plus k1t square minus k1t square by 2. So this term is written here and this term is written here, right? Is equal to 0, right? So now we can further simplify this equation. Now when we further simplify this equation, we will get z square plus k2z plus t square by 2k1 minus 2z plus t square by 2k1. As you can see here, so we have k1t square by 2, so we can simplify this term, so we'll get k1t square by 2, right? So k1t square by 2 minus tk2 and plus 1 is equal to 0. So this is, for example, your equation number 9. Now to determine the values of k1 and k2, equation 9 must be compared with the desired closed loop characteristic equation, right? So the desired closed loop characteristic equation can be formed through desired closed loop poles, and the desired closed loop poles are, what are the desired closed loop poles? The desired closed loop poles are z1 and z2 is equal to this. So now, so we have z1 is equal to 0.875, we have plus 17.9 degree, and z2 is 0.875, we have minus 17.9 degree. So on solving for z1 and z2, we get z1 and z2 are already given, so not solving for z1 and z2. So we'll get the desired. So the desired closed loop characteristic equation is, so we have z minus 0.833 plus j 0.269 into z minus 0.833 minus j 0.269 is equal to 0. So on simplifying this equation, we'll get z square minus 1.67 z plus 0.77 is equal to 0. This is, for example, your equation number 10. Now let us compare equation 9 and 10. So on comparing equation 9 and 10, we get k2t plus t square by 2k1 minus 2 is equal to minus 1.67, and t square by 2k1 minus tk2 plus 1 is equal to 0.77. So we can compare, like we can see equation number 9 here, we have equation number 9 here, we have equation number 10 here. So we can compare the relevant elements, coefficient of z square is 1 both, coefficient of z is compared and the constant is compared, right? So take t is equal to 0.1 second because it is already given, right? So we have 0.1 t plus 0.005 0.1 k2, sorry, 0.005 k1 minus 2 is equal to minus 1.67. So this will give me 0.005 k1 plus 0.1 k2 is equal to, I have this 0.33. This is, for example, equation number 11. And similarly, here also I'll take t is equal to 0.1. So I'll get 0.005 k1 minus 0.1 k2 plus 1 is equal to 0.77, 0.005 k1 minus 0.1 k2 is equal to minus 0.23. This is, for example, equation number 12, sorry. So we can solve equation 11 and 12 for k1 and k2. So on solving equation 11 and 12, we get k1 is equal to 10 and k2 is equal to 2.8. So the required state feedback gain matrix is k is equal to minus k1 k2, that is minus 10 2.8. So this is the answer for this question. That means this state feedback gain matrix will place the closed loop poles of the characteristic equation number 9 at the desired location, right? So how did we solve this numerical? We have simply taken the system. Okay, we have obtained, or either the matrix F and matrix G are given, or we can obtain these matrices if not given somehow, right? Then the first is we need to find out the characteristic polynomial, then we have to find out the closed loop characteristic equation, and then we have to find out the uh, what do you say, the desired closed loop characteristic equation, and ultimately we can compare the required closed loop characteristic equation with the desired closed loop characteristic equation, and we can get the state feedback gain matrix k. So this is it for today's lecture, and thank you so much.